Hey, what's going on everybody? Welcome to my channel AI Solution, where I teach you everything about artificial intelligence. So in this video, I'm going to teach you step by step how to solve a problem like a data scientist. So make sure you watch the video until the end because you might learn something new today. For the purpose of this tutorial, we will use a dataset from Kaggle, and I will walk you through all the necessary steps from beginning to end to solve this task. We will cover data analysis, feature engineering, and training the machine learning model. So if you like my video, give it a thumbs up, subscribe and activate the notification bell to be sure you will never miss a video again. So without further ado, let's get started. Whether you want to implement AI into your business or you just need consultancy from a machine learning expert, I'm the right person for you. From acquiring data till deployment, my multiple years experience will provide you full support which will help you to boost your business. To find out more, check the link in the video description. Okay, so the first thing that we want to do is to download the dataset from Kaggle. So we have to go to kaggle.com, go in the section Compete, choose Titanic, and then register if you haven't already, then go to the section Data, and finally click Download All. So for this video we will use Jupyter Notebooks. So you can either choose to select Google Colab, install Anaconda on your computer, or even use the Jetson Nano and set it up like we did for my deep learning course. If you want to follow along using the Jetson Nano, then you can check out my previous video on how to set up the Jetson Nano for machine learning. As always, I will give you the link on where to download this Jupyter Notebook in the video description. I recommend you to watch the video first and then go and download the Jupyter Notebook and experiment by yourself, or eventually, side by side, use the Jupyter Notebook as well as pause the video and follow along. So what you should expect from this training. This is going to be, as I mentioned, a hands-on project. Then you will understand how to structure a correct machine learning workflow. You will learn some techniques for analyzing data and get a feeling on how a data scientist thinks. What you should be able to do after this training, you should have an understanding on how to tackle a machine learning problem, have a reference of the steps and code needed when solving a machine learning problem, start to develop a data scientist mindset, and this is the most important, and use this as a starting point to dig deeper and properly learn machine learning yourself. So in this training, I will not explain the math behind the algorithms, but if you want to go deeper and understand deep learning in details how it works, you can check out my series on the complete deep learning course. So the agenda for this project is going to be starting with a project description, then we will understand the data, choose an evaluation metric, then we will go into data analysis, feature engineering, then we will see how to select a model, make improvements, and then we will cover the final prediction. So this is the most well-known competition from Kaggle for beginners, the Titanic. So I'm sure all of you know the history about the Titanic, and in this project we will build a predictive model that answers the question, what sorts of people were most likely to survive? So using passenger data, for example, age, name, the gender, socioeconomic class, etc., we will build a machine learning model to predict whether that passenger will survive or not. So in case you might have forgotten about the Titanic, I'm pretty sure this picture is going to clarify that. So we will start by understanding the data. Understanding the data is the first step every machine learning developer should do. Understand how the data looks like, derive some statistics, and make sure you really understand what the problem is. So we will start by importing some libraries. We will use NumPy, Matplotlib, and Pandas, and we will set a constant random seed. This is very important so that we will consistently generate the same random numbers. So we can execute this code. Then we should import the dataset. So we will use Panda for this. So now we will start by visualizing a few rows of the data so that we get an understanding of each column. So we can use this simple one line of code to do that. And we can see that we get different columns and 15 rows. So we can see that the passenger ID is one of the features that we can use. And it's very important to have a header, so what each column means. So passenger ID is just the ID of the passenger, so it will not provide any information. Then there is the feature survived and can be either 0 or 1. So 0 will correspond to no, did not survive, and 1 with yes. And this is the column that we want to predict. Then we have P class, which is the ticket class, so first, second, or third class. Then we have the name of the passenger, the sex, so the gender of the passenger, the age. Then we have the number of siblings or spouses aboard on the Titanic, number of parents and children, the ticket number, fare, the cabin, and embarked. So where did they embark? So we can see, for example, already that in the feature cabin there are some missing values. You can see this NAN, not a number. As well as in the embark, you can see mostly 3 letters. And this stands for the port of where they embarked. C stands for Cherbourg, Q for Queenstown, and S for Southampton. I hope I spelled that correctly. So now we want to understand how many data points we have. So how many columns and how many rows. By executing this code, we can see that we have 891 rows and 12 columns. Out of those 12 columns, 1 is the feature that we need to predict. So we will have 11 features and 891 data points to predict, to train on, and then to predict. Now, for each feature here in this code cell, we can see the number of non-null count, meaning the rows, the data points in which they contain a value and are not empty. For example, age, out of 891 data points, only 714 contains a value, meaning roughly 180 passengers we don't have the data for the age of those passengers. For the cabin, instead, we can see it's very low, so we really don't have much of information coming out the cabin. And also for embark, there are just 2 missing data points. Then we can also check some statistics that are on this data. So by executing this line, we can see the mean, standard deviation, mean and max values, as well as the percentile. Okay, so now we go into choosing an evaluation metric. So choosing an evaluation metric is a critical step in machine learning. Now, in this Kaggle competition and in every Kaggle competition, there is always a provided evaluation metric. But for the purpose of this training, let's assume we would have to define it by ourselves. So in this project, we have to solve a binary classification, meaning it can be either 0 or 1, the output. So let's first see whether the 2 classes that we have, the 2 possibilities that we have, are equally balanced. So as you can see, the 2 classes here are not balanced. And we have to take this in consideration when choosing a proper evaluation metric. So let's compare then multiple metrics to see how they behave one another. So for this tutorial, we will start by comparing 4 evaluation metrics. One is going to be accuracy, the default for this Kaggle competition, then precision, recall, and F1. Now, if you look at these metrics, you can see how the score is calculated. For the accuracy, it's just the sum of the true positive and the true negative divided by the entire true positive, true negative, false positive, and false negative. For precision, we use only the true positive and we divide it by the true positive plus the false positive. Recall is true positive divided by true positive minus false negative. And F1 is a combination of precision and recall. Now, if you don't know what true positives and true negative and so on means, then we can easily understand it with this picture, which is quite funny. So you can see that there is a pregnant woman and a man in a hospital. So here we can see the predicted values and the actual values. So when the actual value is 1 and the predicted value is 1, then it's a true positive. When the actual value is 0 and the predicted value is 1, this is a false positive. Vice versa, when the actual value is 1 and the predicted value is 0, then is a false negative. And of course, when the actual value is 0 and the predicted value is 0, then we're talking about a true negative. So now you don't have, of course, to remember all this stuff. You don't have to know automatically how all of these metrics work. But let's make a simple comparison. So we will see the score of each one of these 4 metrics in 2 scenarios. In case all our predictions are 0 and all our predictions are 1. So by executing this code, we can see that in case all the predictions are 0, accuracy score, so the accuracy evaluation metric, gives us a score of 61.61%. F1 score instead gives a score of 0, and same goes for precision and recall. So there is a huge difference. In case of all predictions, so all what we predict is 1, meaning everybody survived, then accuracy score gives a score of 38.38, F1 score gives 55.47, precision gives again 38.38, and recall gives 100%. So as you can see, there are a few things to notice. Accuracy is not 50-50 in this case because the classes are not balanced. So by having an imbalanced data set, and if you use accuracy metric, then of course this doesn't really resemble the performance of your model. Recall in this case, it's really bad. We cannot really use it because just by predicting always that the passenger will survive will give us a score of 100%, and this is not what we want. Here I would say maybe a precision score is the most appropriate for this example, but for the sake of this tutorial we will stick with the default evaluation metric given from Kaggle, so the accuracy metric. But you see that if you're planning to do this on a real project, you really need to pay attention on which evaluation metric you should use. So now we will start with some data analysis. This is a fundamental step that requires a lot of time, and it can be divided into 3 main parts, if we can say. So one is to derive statistics, so create some plots and charts that will help you to make some assumptions. Then we will go into data cleaning, so we will remove outliers, substituting non-values, etc. And then preparing the data for training. So we will start with deriving some statistics. Let's start with the first question. How many people embark from different ports? And is there a correlation between the port of embarkment and the survival? So this is one of the many questions that we will go through, and we will try to answer that just by using the data. So we will really visualize the data, make those checks with the code, and see what the result is going to be. So by executing this code, we can see that most of the passenger embarked in port S. Now we can see from this plot the count. So we can see, as we mentioned before, was like in a percentage, 72.2% was in port S, and here we can see the count, so really the number of passenger. And we can see that it's also here pretty much in balance. Most of the passenger embark in port S. Then let's see if there is some kind of correlation between where the passenger embarked and if they survived or not. So we can do this by executing this code. Okay, as you can see in this plot, most of the passengers who embarked in port S or in port Q had a higher chance not to survive. Instead of the passenger who instead embarking in port C, they have a higher chance to survive. So now let's make a simple prediction to see our score. Let's say that if the passenger embarked from Queenstown or Southampton will not survive, else he will. So we can execute this code to do this. And as you can see, I just filtered the data based on the passenger who embarked in port C. So we can execute this. And then let's print and see the score. Okay, so we can see that the score is also not great. It's still 63.6%, but it's higher than before when we were making a prediction that none of them would survive. Okay, so now we go into another question, which is, does survival depend upon gender? If you've seen the movie, of course, the priority, at least in the movie, was given to babies and women. So let's see, based on the plot, if that actually is the reality. Yeah, so we can see that actually female have way higher chances to survive compared to men. So this is already a pretty indicative way on where we should make the prediction. So whether it's a female or a male. Okay, so now let's make another prediction, which is also pretty straightforward. So if the passenger is a female, then it's going to survive, else it won't. So we can execute this code. So this starts to be quite a good number. Let's see if there is any correlation between the gender, port, class, and survival. So by executing this code, we can see first, we analyze the class, and we see if the class of the passenger is somehow related to the chances of survival. And as you can see, it is. Passenger from the first class, they have a higher chance of survival, above 50%, while the mid class, so the second class, they're about to 50%, and the third class, so the poor people, it's pretty low, the chance of survival. So this is also very indicative that rich people have a higher chance to survive. Now let's combine this plot with gender and the port. Okay, so this is quite a big plot now, and we have several plots actually. So we can see that male of the first class survived in port S are below 50%. So we get around 35% rather than 65% who didn't survive. Male of second class, still in the same port, they have a lower chance of survival. As you can see, it's like about 15%, and is about the same, a bit less for male in the third class. For female instead, we see completely opposite. So female of the first class, embarking port S, almost all of them survive. So we get a 95%. In the second class is about the same, is 90% the chance of survival, rather than the third class instead, it's still, let's say, is way less now. So we get like 60% chances of non-survival, but it's still better than the male, compared the male to the same characteristic of whether they are embarked in port C. So now let's see the differences in the other ports with the same structure, and we can see that also in port C, for the male at least, there is not much of a difference. There is a bit more chances of survival for second and third class, but overall it doesn't change much from the previous port. For female is also about the same, but we can see that is almost 100% the female of the first class embarking in first port. The female of the second class embarking port C, all of them survived. So this is pretty straightforward. So we can see the consistent higher chances of female to survive. And in the third class, we get instead, as always, lower probabilities, but still way better than the compared male version. So now we go into port Q, and we can see that all of the males here did not survive. So none of them. Same also for the males in second class, and for male in the third class, a very, very few of them could survive. So this, for a male at least, whoever embarked in this port really didn't have any chance of survival. Whether instead for female, we can see that it's 100% almost everywhere, except for third class, as always, that he has still a 70% chance. So what are we gaining from these plots? We can see, as we saw, the female had way higher chances of survival compared to men. We can see some pattern also that in port Q, every man didn't have any chance to survive, so this is also indicative. And we can also see that female of the third class, they have a way lower chances to survive compared to the other two classes of female. So now let's go to the third question. Does survival depend upon age and gender? So as you can see, we're always going forward. We start to analyze one feature at a time, and then we start to combine multiple features and see whether by combining those features together as a filter, we get some additional information. So let's see if it's true that women and children had priority, like in the movie. But we can use the graph above, so what we saw before, to filter some more cases. For example, men have some chances of survival only if embarked in port S or C, because we saw that in port Q none of them survived. And women have chances of non-surviving if they are poor. So this can also be used as a filter. So we want to filter this data, so we got already, okay, female in the first and second class, almost all of the time they survived. And for the men, we analyze only the whoever embarked in port S and C, because in port Q, all of them died. So we can execute this code. Okay, so here we have the two plots. As we can see, we have the female and their age, as well as the male and their age. Of course, as I mentioned, those are the two filter data, so this is not the entire data. So those are the female of the third class, and those are the male not embarking port Q. So as what we can see here is that babies up to roughly 6 years old have a pretty high chance of survival. We can see from both from the female side as well as from the male side. Then regarding women, we can see that between 13 years old and 27 years old, women of the third class have a higher chance of surviving. Instead, for the men, we don't have a clear understanding. At least there is not a clear division regarding the age. So we can see that most of them didn't survive. So I hope you guys are getting what I'm trying to bring you. So we were starting from analyzing one single feature at a time and see if that was somehow correlated to the task that we were trying to achieve. In this case, surviving or not surviving. And then starting to build a kind of a tree structure. So combining multiple features to see whether we can get some insight. And this is very important because this first gives us an understanding on the data itself, and we're trying to find some pattern. And when you go into a real world application, then you definitely see, you need to show your assumption. You need to prove that what you assume is correct. So instead of just making hypotheses, you ask questions, you check whether those, how to answer to those questions only based on data. Okay, so now how can we analyze this further? We can see now that for female, we have a pretty good understanding based on their class, so if they're rich or mid-class, and also regarding on their age, whether they have a high chance of survival or not. For the male, it's still ambiguous because we can see that here there's not a clear distinction. So this brings us to the next question, which is, do younger rich men have higher chance of survival? So here we just see men not embarked in port Q, but there is no clear division except for babies. Let's see if there is a division also based on class and when we plot all of this together. So we can execute this code. Okay, and as you can see now we are getting some pretty good understanding on the data. Now it's pretty visible where is the higher chance of survival. So as we expected, so as we mentioned babies, of course, but still we see that there is some kind of not much of a chance of survival for babies of the third class, which is very sad also. Instead, for the mid-class, the babies and the young boys, and also for the rich class, they have all of them survived. And also we can see that young rich men actually have a pretty good chance of surviving. So now, based on all what we have seen during this step of data analysis, let's try to make some predictions, okay? Let's make some prediction based on just what we saw, analyzing the data. So we will apply some filters to the data. So we will say that all non-poor women will survive. That's the first row. Then we will say that poor girls up to 6-year-olds will survive. Poor women between 13 and 27 years old will also survive. Non-poor boys, so rich and mid-class boys up to 12 years old, not embarked in port Q, because we saw all of them didn't survive, will survive. And then rich men between 25 and 37 years old, not embarked in port Q, will survive. All the rest will not survive. And then we scored our function. So we can execute this code. And we can see that now the score went quite much higher. So remember, we started from a very basic classification. So we started to say, okay, nobody will survive and was very poor. It was about 61%. And now we reach 82% just by simply analyzing the data. So here there is no machine learning yet involved. We're just purely seeing the data, checking each feature, how it works, and how it affects the survived class, and we got to a pretty good point. So this is pretty awesome. So far there was no machine learning. Still, by just analyzing the data, we could get pretty good performance. There is still something to notice, which is that so far we are analyzing the training data and we are making prediction based on the training data. So we are creating our algorithm. So the score that we see here is not our final score, of course, because we are basing everything on what we see in the data. But then we need to see later on in the test data how this algorithm performs. Okay, so now we go into data cleaning part. So cleaning the data is the most important step when using machine learning. If you don't clean the data, you will get not only suboptimal results, but you might even confuse the algorithm, making the improvement step even harder. So this is very important that the data is clean before training with machine learning. So, but what do I mean exactly by data cleaning? In data cleaning, I included all the steps to make sure that our algorithm can train itself without being penalized by outliers and or missing values. So as we saw at the beginning when we were analyzing the data itself, there were a lot of missing values for the feature age and for the feature cabin. And also by data cleaning, we need to find some outliers. So we need to see some exceptions, because of course also in this data set there is some chance of luck, right? So it was not like a clear separation on who survived and who not survived. Some was also based on luck. So let's start by dealing with the missing values, the NaN values, not a number. So age is a feature where there are many missing values, as we saw at the beginning of this notebook, but we also saw that age is an important factor for predicting the survival of a passenger. So for this reason, we will fill the NaN values with random numbers, which are computed based on the mean age value in regards to the standard deviation for each gender and class. So what do I mean by this? How do we fill up this NaN value? If those values are not inside the data set, we can either ignore them, so ignore those data points, but it's going to be a shame, right? So we don't have already much of data, we want to keep this data, but of course we cannot just put some random numbers inside or just put some mean values inside. Why this? Because we saw that it's a very important factor for us to understand to make a prediction on whether the person survived or not. So what are we doing now? Now we are going to split and analyze the distribution of the age feature based on the gender and the class, right? So we can execute this code first, and we can see that we get way different results according to whether the gender is a male or a female and the class of that passenger. So we can see that female of the first class, they have a mean age of 34, so 34 years old. With the standard deviation, we can see that it's almost pretty constant everywhere, but the mean is where actually most of the change appear. Instead, we can see that women of the third class, they're around 21 years old as a mean. Whether instead a man in the first class, the mean is 41. So now imagine if we would have just put the number, for example, the mean age on the entire data set in all of these missing values. This wouldn't have been good. Wouldn't have been good because, as you can see, the mean change is based on some other characteristic of that person, right? So now we can use those statistics that we just derived to compute, as I mentioned, a random number for the age based on those statistics, right? So we can execute this code, and we can see that also here was meaningful to have made such a division. Why? We can see that we have only 9 missing values of female in first class, or women of the first class, and only 2 missing values of women in the second class, and 42 women of the third class. And men in the third class, they have 94 missing values. So as you can see, we couldn't have just put some mean value for the feature age, but now it's more appropriate because it's based on the distribution related to the filter data. I hope this does make sense for you. If you have any question, for sure, you can ask in the comment down below, and I will try to explain the best way that I can. But I hope that this makes sense for you guys. So now that we have replaced all of these none values, we have also to replace the 2 missing values in the feature embark. There were only 2 missing values. So since there is only 2 missing values and there is not much in there, based on what we saw, the majority of the passenger embarking in the port S, so we will fill those 2 missing values and replace it with value S, so that like they embark from the port S. So we can execute this code, and now we can run again the data.info so that we get an understanding on where if the changes that we made are applied to the data set. As you can see, all values are filled up except for the feature cabin. But as you can notice, from the information above, there are 687 missing values out of 892. For this reason, and also for the fact that the cabin is also related to the class of the passenger. Why that? Because of course, if you were purchasing a more expensive ticket, then you would have been on the top of the boat, right? Instead, if you were poorer, then you would have been like more on the lower side of the boat. So for this reason, it is better to ignore completely this feature. Why? Because most of the data is missing. So we don't want to use data which has too much of missing values inside, right? Also, passenger ID and ticket can also be discarded because they don't provide any useful information. Now, as a disclaimer, I'm not sure if we could retrieve the cabin number based on the ticket. So far, I couldn't find anything that would have made sense. That's a possible solution. So if we can give the missing value in the cabin correctly, so instead of just guessing or putting something in there, that's the way to go. But since I couldn't find any correlation, then we will discard those 3 features. So with this simple line of code, we can discard everything. Now we need to remove some outliers. So in this case, we can consider age as a possible feature containing outliers. If the passengers were old, poor, and survived, Well, as we saw, is an exception, right? So we can run this code and we will remove people which are above 60 years old, they survived and they are not from the first class. Or they are above 70 years old and they survive. Why? Because we saw that the priority have young people or rich or even or also women. So we can execute this code and we can see that we found 3 outliers. So one woman from the 3rd class that survived. She was 63 years old. And then we can see other 2 males, so 2 men, one even 80 years old that survived. Okay, so now we reach the point in which we are preparing the data for training. So machine learning algorithms don't work with strings, so they use only numbers. So everything has to be converted into numbers. For this reason, we will convert the feature sex and embarked into categorical features. Name is going to be left as is for now. We will use it later during feature engineering. The feature P class should be categorical too, since there is no correlation between the values and the category. As we saw, the feature P class contains only values 1, 2, and 3. So instead of using this as a numerical feature like this, we can transform it into categorical feature, meaning we can transform this feature into rich, mid-class, and poor. At the end, that's actually what it is. So we will first visualize the data, how it looks like now. As we can see, we have, except of the feature survived, it's our label, we have P class, name, sex, age, siblings, spouses, parent, children, fair, and embarked. And after our data transformation, we can run this code, and we can see that now we have more features, right? We transform those features. Now we have still name, age, siblings, spouses, and parent, children, and fair. But we can see that now we have embarked in C, Q, and S. Before it was in one feature. Now we have encoded this information into 3 features because, as I mentioned, we cannot process strings. Of course, now we have is female is a new feature. Because we don't, of course, if it's not a woman, it's going to be a man. So we don't need 2 features for that. And then we can see that we have rich, mid-class, and poor instead of the P-class feature. So to give you a quick recap in case I was going maybe too fast, machine learning cannot process strings. It has always to work with numbers. So whenever we have a string in a feature, we need to transform into numbers. How do we do that? By encoding this information in a binary fashion. So we could see that embarked as values C, Q, and S, and now we have 3 features where 0 correspond to it's not embarked in C, and 1 it correspond to it was embarked in the port C. So we can see, for example, in this line, that person was embarked in port S. Same we had to do for the gender. So now we created one feature is female. So 0 is going to be it's a man, and 1 of course is going to be it's a woman. And then we also transformed that feature that was 1, 2, or 3 for the class, for the ticket class, into something more appropriate, because there was no much of correlation between the value itself of 1, 2, and 3. Instead, was something more categorical. So is a rich man, is a mid-class, or is a poor man. Something that makes sense instead as a value is the age, right? So the age is something that makes more sense to have it as a number and not as a categorical feature. Same applies also for the feature fair. Okay, so now we go into the fun and complicated part of feature engineering. So this part is where we try to create new features out of existing features. This requires some intuition and can make the difference when trying to increase the last roughly 1% or 2% of model's accuracy. So it's important that we never create new feature from simple assumptions, okay? So we need to engineer those features, but they have to be related on the data that we are using. So we cannot invent anything new. Otherwise, we will penalize the performance of the model. So let's see what information we have which haven't been touched yet. We have the feature name, the feature sibling and spouses, feature parent and children, and the feature fair. So to begin with, we can see that we have those features, siblings and spouses and parent and children, that can actually be combined and considered as relatives, right? So it doesn't really matter if we had whether more siblings and maybe no parents, or more children and spouses. This shouldn't be relevant for the survival. What makes more relevance is that if how many relatives you had with you traveling with you. So we can run this line and we simply create a new feature. Now that we have a new feature, we should use it to see if we can retrieve more information out of it. So, do the passenger have better chance of survival while traveling alone? Because now we can clearly see who was traveling alone and who was having some relatives with himself. So we can execute this code. And here we have the plot, and we can see that passengers had a higher probability of survival with 1 to 3 relatives. As we can see here, is above 50%. But a lower one if they had more than 3 or they were alone. As you can see here, whoever was traveling alone doesn't have much of chance of survival. And also when they start to be 4 and above, they start to be not having much chances of survival. So here we need to also see whether this makes sense to us. And one possible thesis is that families have a higher chance of survival than singles, because they are better able to support themselves and were rescued with priority, right? So people were trying to rescue probably more like a mother with children and a husband, so as a family, instead of picking people randomly, right? However, if the families are too large, coordination is likely to be very difficult in an exceptional situation. So this also makes sense. When the family is 10 relatives plus the passenger itself, so 11 people, to put them together and save them, it starts to be more complicated. Also, as trying to help each other start to be more difficult, especially in those complicated situations. So as we just saw, there were passengers with many relatives. So it would be more appropriate to divide the fare by the number of people in order to get a fare per person. So we can create a new feature calling it fare per person, where we divide the amount by the number of relatives plus the passenger. So we can simply do it with this line of code. And so now the only remaining feature that we haven't touched yet is the feature name. So where we have the names of the passenger. We can see also that names contain also titles in the name. So Mr., Mrs., Doctor, Captain, and so on. So maybe we can get the titles from the names and build a new feature out of that. Let's see. We can execute this code. As you can see, there are quite a lot of different titles in our dataset. So we will only consider titles with more than 10 cases. All other we will assign to the category miscellaneous. So we can divide it and we can create a new feature, title, and then we can see some statistics out of it. So we can see that whoever had the feature, the title miss, had a 70% of survival. You can see the 70% out of that. So, and whoever had the title misses had a 79% of survival. Whether instead with man with titles on Mr. at only 15%, and then miscellaneous at 34%, and master 57%. So once again, those are strings. So we need to convert those strings into one hot encoded features. So we can do this with this line of code, and now we can see what the result. So as you can see, now we get 888 data points because we removed the 3 outliers from before. And as we can see, now we have the feature survived, name, age, sibling and spouses, parent and children, fair, embarked like before, is female, rich, mid-class, poor. Then we have relatives, the feature that we create, fair per person, and then title master, title miscellaneous, title miss, Mr. and Mrs. So now we have a total of 19 features, because the feature survived is going to be our label. So we have quite a good number of information now. Now, something also interesting to analyze is that now that we have 19 features, is also quite a good number, because most of the machine learning algorithms can process this amount of features, which are also at the end dimensions. If we would have had hundreds of dimensions, then not every machine learning algorithm can process such amount of information. So we might end up to having problems to train such an algorithm. But 19 features is quite a good amount. One thing to notice, have you noticed that we haven't even opened the test dataset so far? This is very important. So this Kaggle competition allows us to use information from the test dataset. Usually it's not the case. So usually they give you only the training data, and then they just give you a sample of the test set, where then when you submit the proposal, the submission, when you submit the results, they just replace the data during the submission. So you don't even see the test data. And that's actually the way it should be. So you cannot consider, machine learning is something very tricky. You cannot consider the entire data when you are creating an algorithm, machine learning algorithm. Why this? Because you want to make sure that it generalizes well when it sees some unseen data. But this does not only apply for training. It also applies for the feature engineering, for the information that you have used. So you cannot use information from the test dataset. So in a real scenario, what you would do is you would start to understand the data. Then you will split this data. Now the split is also a tricky part. Can be done randomly or can be done with some meaningful sense. It depends on the case. But for sure, you don't want to touch this test data. So it has to remain standalone on your hard drive, and you have to work only using the training data set. When you test it, then you test it on the test data set. So now that we clarified this part, we can proceed. Now, a way that we could have also kind of hacked this competition is by considering also the names in the test data set. For example, we could identify family names of passenger and then see if there are any family members that are present in both the training and the test data set. In a real world task, we would not have the opportunity to do this. Or better, we might have the possibility, but we definitely don't want to do this. So, also, Kaggle usually, as I mentioned before, doesn't give you this possibility. If instead we are talking about machine learning task in a non-competition, we could do this, but it would be absolutely wrong. As I mentioned, we should never kind of bias the information, right? So we should consider only the training data set and then apply everything, the same technique on the test data set. So you want to make sure that your algorithm works every time. So for this reason, we will not do it. So we will not check the names, the family names in the test dataset. This is something that you could use if you want to increase the score in the competition, but for the purpose of this training, we will not do it. So now, since we have the feature name still, we can simply drop it. So now we will extract the labels out of the dataset. So just take the feature survived and then divide our dataset into 3 groups. A dataset without feature engineering, so without the features that we created during that section. Dataset without the feature used during the feature engineering step, so we use only the engineered features and we discard the others. And then a dataset with all the features combined, so the 19 features that we saw before. So why am I doing this? I want to make sure that the features that I created really help the algorithm to learn instead of just making it more confused. So we really want to test whether this really works. So first of all, I just want to save some space in memory, even though it's very less. We will just change the data type of each data point by its minimum. So we can run this code. And we can see now that the memory usage is very, very minimal, 21 kilobytes. So now we just divide, we will divide, as I mentioned, the labels from the other 3 dataset groups. So now we enter the model selection part. And this is the point in which we have to choose a machine learning algorithm for this task. Out of all algorithms, for sure we can choose only the ones that work for classification tasks, but there are still so many. So then how do we choose a machine learning algorithm? Here, experience, of course, helps a lot. Unfortunately, we can't say which algorithm is going to be the best without having tried it. So usually boosting algorithms like XGBoost, AdaBoost, etc. work quite well out of the box. But of course, we have to try them out. If you want to choose an algorithm, the only way to do it is to try many different algorithms and compare their performance based on the chosen evaluation metric. But there are a couple of things to keep in mind. Different evaluation metric can let you choose different algorithms. So this is why it's very important to know which evaluation metric is more appropriate for your task. The training data and testing data has to be exactly the same for all algorithms. Of course, you cannot train one algorithm with some data and another algorithm with some other data. We must shuffle the data multiple times and average the results across multiple runs. So we need to train on a part, we will have a training data set, because as I mentioned, the test data set cannot be touched, so never be confused. Also during the model selection, you can never check this on the test data set, always check on the training data set. So we can divide this training data set into multiple chunks, and in which you repeatedly train the algorithm on different chunks of this data. So you will use a part of that data to train and another part to make a validation. And then repeat this multiple times and then average the performance that you get out of it. And as a fourth point, we must ensure that the class ratio in the training and testing set is preserved, right? So by testing set, in this case, I mean when we split it into training and validation, right? So, of course, also in the test set, now we are not touching the test set, but when you split in case of a real-world scenario, if you are not doing a Kaggle competition and you need to divide the test set, then also there you need to check whether the classes are actually balanced. So before we begin choosing the algorithm, let's implement the algorithm we made before, so the coded one, into a function for comparison against machine learning algorithms. So we will call this my predictor. It's a simple function where I just filter like I did before. So I can execute this code and I instantiate the function, and then I just score my function only on the training data set, of course. So when I run this, I get a bit better performance than before, 82.5 instead of 82%. And this is very good. The reason why I also increased a little bit is because we modified the age, right? So there were some missing values and now we filled up some values. And we can see that it's getting better, so we filled it up properly. Now we will list down all the algorithms we're going to try. So as you can see, I imported quite a big amount of classifiers. We can see Bayesian classifier, random forest, AdaBoost, gradient boosting, logistic regression, decision tree, stochastic gradient descent, and support vector machine. And I just collect them into a dictionary. And as you can see, we have created also the number of shuffles. So how many times we're going to train and average their performance. So 10 times. And then we also have some scores so that we will average the results. So we can execute this part of the code. And now that we have all of the algorithms listed, we create a for loop and train each one of them. To take care of the points previously mentioned, we will use a function called stratified k-fold, which provides train and test indices to split data in train and test sets. In this case, test sets means validation set, because the test set, which is coming from the competition itself, we still didn't touch it. So we're just splitting the training set into groups each time. In this case, 10 times. And how does it split this data into training tests? It does it by preserving the percentage of samples for each class. And this is very important because, as I mentioned before, we want to make sure that if we have a certain percentage of non-survived and a lower percentage of survived people, we want to make sure that we train on the same kind of distribution, both for the training and the validation, right? So the way of doing this with Python is pretty straightforward with scikit-learn. As I mentioned, we can use this stratified k-fold. Then we can use also something called standard scalar as a preprocessing step. So as you will see later, when you train, some kind of algorithms need the data to be in a certain range, right? So, for example, we have the feature age, which gave us values between 0 and roughly 70 or something like that. And some algorithms cannot train such a sparse data. They want to have it more in a closed range, right, to converge faster. So that's something to keep in mind. You can either use a preprocessing step, like some scaling technique. You can not use it, you can use different one. So I invite you to try it out, some other combinations. So not only standard scalar, you can go on Google and check for scikit-learn preprocessing step and you will find many of them. So the first thing, I want to guide you very quickly through the code. So in this part, we can see that we choose the dataset type. As you remember, we have 3 datasets, we divide into 3. So we will start with the base one, so the one without feature engineering, because as I mentioned, we want to make sure that we get better results when we create some engineered feature. Then we create this stratified k-fold class, so that we can every time divide the data and then train and average across the performance. So as you can see here, the first part is going to just to split the data. And then we iterate through the algorithms that we're choosing. And we will record also the training time. Why this? Because sometimes, as you will see later, the training times matter. So when you have a lot of possibilities that you need to try, having a long training time might be a blocker. So if you need to train for a long time, and then you want to try a different combination, this is all time that you're kind of waiting until it's computed. And another thing that we want to keep track of is the inference speed. So also how much time the algorithm takes for making a prediction, because depending on the application, you might want a very fast algorithm. After that, as I mentioned, some algorithms work better when the data is scaled. So we will use, in this case, the standard scaler when we have gradient boosting, logistic regression, or using supported vector machine models. So as you can see, then we have a training part and a prediction part. And then we just derive the information and print the score as well as the training time and the inference time. And finally, we will print the average accuracy over the 10 training steps. Okay, so we can execute this code. This is going to take a little while, but as you can see, we can already see that some algorithms, the training time is way higher than others, and inference speed as well. So when using support vector machine, usually takes longer, right, instead of a logistic regression. So we can see that is keep on testing on all batches, but now we reach at the end, and we can see that so far we can see the gradient boosting achieving the highest score. And then this is the average score, as I mentioned. Then we have logistic regression. We have the bagging algorithm, then the random forest, then logistic regression, and then all the others. Keep in mind those numbers. As you can see, we get the highest as 82.43, but then the other are around 78 or 80 or 81. So this is the performance that we get from the data contained without the feature engineering part. So now we want to test first that the data, when we engineer those features, really helps the performance of the models. So we can just go up again and change this variable so that we can get the other data set. And we run the test again. So as you can see, the training time might be even higher if we have more feature for the supported vector machine, because basically those resemble in more dimensions, so more dimension, more problems actually for training, more complexity, I would say. So now again at the end, and as you can see, we get better results. So at least for some algorithms, we get way better results. We can see gradient boosted now achieve 83.67%. Then we have logistic regression who score 82.76. Bagging using support vector machine scored 83.33, and bagging the other version, so with the decision tree, scored 81.98. So we can see that we get overall an increase, except maybe for random forest and AdaBoost using support vector machine, but all the others get an increase. So meaning the features we have created really helps to make better prediction. This is very important to double check that we did this correctly. Okay, so now it's time to train with the data set containing all the features. One thing that I changed though is to comment out the bagging support and vector machine, because it was taking too much of time to train. So it really is not feasible. I start to struggle when having so many features. So we will still use all the others, but we just will ignore for this time this one. So we can execute this code. Okay, and as you can see here, we get for some algorithm a bit better performance, for example, for logistic regression and gradient boosting. One thing to notice though, this is something that you will figure it out by experience. Some algorithms handle better when they have a few more features to use, and others might tend to overfit very bad, or even having trouble to train, as we saw with the other algorithm. So in this case, we can see that even though gradient boosters get a bit better score, since it uses a decision tree classifier, it's still better not to have too many features containing kind of similar information than because we start to overfit. So instead, logistic regression can handle more feature pretty well. So from the above code, we learn quite a lot of information. So the first is that depending on what data we use for training and testing, we get very different results, as we saw from the 3 data sets. By doing feature engineering and reducing the total number of features, we can get better results, because except logistic regression, all the others perform better with fewer features. When an algorithm fails, another might work better. This is something that we can see here, for example, on each batch. For example, we can see that on the batch number 10, logistic regression was better than gradient boosting, but for the batch number 9, gradient boosting was way better than logistic regression, and we can continue like this. So meaning, depending on what you train and what algorithm you use, you might get sometimes better performance, sometimes worse. So this is already a hint. We might even combine multiple algorithms to get the best possible performance. And the fourth point is that if we have timing constraints on training or inference speed, some algorithms might be not appropriate. Because for now, remember that we were just having 888 data points, but when you start to have millions of data points, then you will see a difference in training. You can see logistic regression is super fast. If you use AdaBoost instead, it's way slower. Support vector machine is even worse. So at that point, also depending on what your application require, you might choose an algorithm over the other. So out of all of this, what we will use then is going to be the bagging algorithm using the decision tree classifier, the bagging algorithm using the supported vector machine classifier, because we saw that anyway was working very well when using the dataset containing only the feature, the engineered features. Then we will also use, of course, gradient boosting, which seems the best so far, as well as using logistic regression. So we will use those 4 algorithms for further analysis. So now we go into the step of improvements. So now it's time to make some improvements, and we will first look for the optimal parameters for each chosen algorithm. In this case, optimal out of a certain amount that we can try. We have no guarantee of saying that those are the best parameters for those algorithms for this data set. This is absolutely not possible. Instead, I also want to encourage you to try different parameters. Now we will go through and encourage you to try it on your machine, different parameters, and see how it behaves. So afterwards, we will use the whole training data to train these algorithms with their respective parameters. So the best parameters that we have found for that algorithm. These 2 steps, so searching for parameters and training again on the entire data, can be combined using the grid search CV from scikit-learn. So it's a small module. So finally, at the end, we will combine the output of all 4 algorithms for our final prediction. So we will not rely only on one algorithm, and this is also something very important to know. As we can see, as we saw, if we rely only on one algorithm, sometimes it might perform better or worse. Instead, if we rely on multiple algorithms, usually it tends to perform better. So we will just keep the original data in those 2 lines. So we will call them X feature engineer original and X all original. And then we scale the data. Okay, so using the standard scaler that we saw, because those 4 algorithms require this scaling. You're encouraged to try, as I said, a different scaler and see also how they perform. So we can execute this code. So we will start by optimizing the gradient boosting algorithm. So as you can see, it's pretty straightforward. We initialize the gradient boosting algorithm. I already filtered out some parameters to use for this algorithm. Of course, you can try different ones. Then we have a selection of parameters that we want to try. So the number of estimators, the learning rate, the minimum sample split, and the maximum depth for each estimator. In this case, the estimator, as I mentioned, is the decision tree. Of course, what is going to happen now? We have 10 samples, so 10 splits, 10 shuffles and splits, as you can see is set up here, that variable, in which we do exactly what we did in the previous step. So we go through the entire data, we split it into training and validation, and then we see the performance of that algorithm on that data, and we average those performance across those 10 testing. And it will do for each possible combination. So we will use one-time number estimator 40, learning rate 0.01, minimum sample split 8, and maximum depth of 3, and then all the possible combination in a brute force manner. So you will see that now the number of possibilities start to be quite a lot. We can see it's basically 3 times 3 times 3 times 3, and we get 81 possibilities. And remember that we're going to train the algorithm 10 times for each of this combination, meaning we will go to 810 times that we train the same algorithm. So that's why it's very important also to know how long it takes for training. So we can execute this code. As you can see, it's also telling you it has to train for 810 times. It's gonna do pretty quickly, but I will pause the video and continue when it's done. Okay, so now it's done, and as you can see, at the very end of the training, we get the best parameters for the algorithm based on what we've chosen. And it's also stored in a variable called best GB classifier. Okay, so then it's time now to find the best parameters for the estimators in the bagging classifier. So the bagging classifier uses some estimators like for the gradient boosting classifier. And we will start by first training those estimators and then find the best parameters for the bagging classifier itself. So it's going to be a two-step process. So we will start by initialize the classifier, in this case support vector machine, and then do the same procedure like we did before. So we can execute this code. This time is going to be way faster, 360 possibilities, and in this case it's already done. So then we get this best classifier out of all the possibilities that we have tried. Now we need to also test the other bagging classifier, which use the decision tree classifier. So we will do the same procedure also this time with several parameters, and as you can see, the code is exactly the same. So we can run the code. The difference is only that one bagging classifier, if you remember, one uses the supported vector machine as a base estimator, and the other one used the decision tree classifier. That's why we're training first the estimators by themselves and finding the optimal parameters, and then we go into the bagging classifier itself. As you can see, we get the best parameters also this time, and now we can optimize both bagging classifiers. As you can see here, there is not many features that we need to optimize, parameters, that you have to optimize. You have only the number of estimators and the maximum features that we can use. So we can execute this code again. This is also going to be quite fast, but not too fast, because it's using multiple estimators for this prediction. But as you can see, it's done. If you get this warning, don't worry. The warning is pretty much straightforward to understand. It says convergence warning, solver terminated early. Why is this happening? Because during our optimization of the supported vector machine classifier, we saw that the best parameter was maximum iteration equal to 600. That means that after 600 iteration, the supported vector machine stops its optimization. So when you get something like this, that means, okay, when it keeps on trying everything and say, okay, it's not converging, so the performance are not optimal. But you can ignore, you can change this. As I mentioned, you can also try different parameters. Then there is this other bagging classifier that we need to test, and here we are gonna make some few changes. As you can see now, we have also the base estimator, and I pass a simple decision tree classifier as estimator, as well as the optimized one that we found before. The reason why I'm doing this is that by using, for these examples, if we use too many decision tree classifiers with the best solution, let's say found from one single classifier, this tends to overfit. So what you can see here, for example, is that the maximum depth has been settled to 5. Instead, the maximum depth found before was 6. So we are not using exactly the same. We are trying to reduce the capabilities of this base estimator so that we try to avoid overfitting. So those are all tricks that you will learn by either trial and error or also by experience. So we will continue the same procedure as before. I just wanted to tell you exactly what changed instead of the previous section. So now this is also done. And then we optimize the logistic regressor algorithm. So we can execute this code. This time we have lots of fits, 2,700. But if you remember, this trains very fast. So we don't have much of time to wait. As you can see, it's going very, very fast, and it's done now. Okay, so now that we have found the best parameters from the one available for all 4 algorithms, we can check the accuracy on the training dataset for each of these algorithms. Now, a quick disclaimer. In this case, we check the accuracy again on the training dataset, even though the algorithms at the end have been trained on the training dataset. Here, in a normal scenario, we should have tested the performance on a validation dataset. Since our dataset is very small, we can't really split it. This causes some problem because when it trains, it doesn't see so many examples, so it goes very easily into overfitting. But here, we need to be very careful because the accuracy might go high, but it's difficult to detect whether the model are overfitting or not. So in a best scenario, let's say in a usual scenario, we should test the performance on a validation dataset on each of those 4. In this case, since we don't have it, then we will use the training dataset, and then right at the end, since we also don't have the labels for the test dataset, we will see how they perform and then maybe do this process in an iterative way. So anyway, let's see the performance for now. So we execute the code, and we can see that we get gradient boosting classifier almost 85%, and then bagging classifier 85.14%. Then we get a logistic regression with 83.33, and bagging classifier, the second one is the one who uses the support vector machine as a base estimator, gets 83.67% of accuracy. So all of them improve their performance from the baseline that we started at the beginning. So this is also good. But now we need to combine those 4 models in the following way. So first, we predict the probabilities of survival for each data point using all 4 classifiers. Then we weight the probability of each classifier, so how much importance has the estimation of that classifier. We adjust the weights of each classifier using a random search. You will see the codes down below. And then finally put all together for the prediction. So what do I mean by that? We will start in this block of code. We predict the probabilities of each of the classifier. So it's not going to be a simple survival or non-survival. Instead, it's going to be what is the probability that that specific passenger would survive or not survive. So all the probabilities will be between 0 and 1. And we will multiply that score by the weight in which each of these classifier has. Then we combine, as you can see at the beginning, we start with 25% of each classifier to get the final score. So we combine the prediction of every classifier, we weight them, and we at the end we pick the best, so who has the highest probability. And we adjust the weights of these classifiers in a random search. So we iteratively for 1 million times, we just choose random weights and then keep on repeating this process. So we evaluate the score, and then if the score is higher, we will save those weights. And we do this in a consecutive manner. As I mentioned, also here we are using again the training data set to see the score, okay? So instead, what we would have to do in a real scenario, so in a production, let's say, we should use the validation data set to do this operation. We cannot use the test data set. The reason why is that you might have some bias toward the best optimization for the data set that you're using in this case, since you're just trying to see which is the highest score available for that specific data set. That can still be a bias for that data set. So test data set, as I mentioned, should never be touched for those operations. Instead, we should use always the validation data set. Since the data set is too small to be divided, then this again goes into an iterative process when we later on we will combine the performance of this prediction with the prediction on the test data set. So let's execute this code. And as you can see, every time it finds a better score, and those are the values for the weights. And now it's gonna continue until the end. So I just pause the video and we will continue once it's done. Okay, so now it's done. And as you can see, now the best score is 85.36%. So we get it up here. And those are the weights that we found for each classifier. So as you can see, the score is a bit higher than before. Before was 85.14 when we were taking the single bagging classifier. And it doesn't seem maybe a big of a change, but it's still an improvement. And also what we can see is that most of the relevance, most of the importance comes from the first classifier, which is the gradient boosting classifier. So this is also indicative. What does this mean? This means that this classifier is the one who's most sure about the prediction and is also correct about this prediction. As I mentioned, remember, in a real scenario, don't do this on the same trained data set. Use it always on the validation data set. I can't stress this enough. It's very important. So now, before creating everything for the final prediction on the test set, let's visualize what these algorithms consider most important for making a prediction. So this is also very important. We want to visualize what is the importance in the algorithm. So what he thinks is the most relevant feature, or like the most relevant features for making the prediction, and see whether that makes sense from what we analyzed before. So we can call this function, which is going to show in a plot the relevance for each feature for each classifier. So this is the function, and we can run the first one, which is going to be the gradient boosting classifier. So the green one is the relevance for the feature itself. Maybe I can zoom out, zoom in a little bit. You guys should see better. And as you can see, it gets the title Mr., considered the most important feature, which is tied with the is female feature. So what we're checking at the beginning also here makes sense. It wants to see whether the passenger is a male or a female. And here we can see that it's doing the same. It's kind of implicitly getting also from the title Mr. Of course, title Mr. cannot come from a woman. And then it also check if the title is Miss, so if the woman is married or not. Also here can be correlated with if the person is traveling with many relatives or less relatives. This is an assumption that I'm making, but kind of makes sense. And then also here uses the fare per person to estimate whether the person is rich or not. It's more specific than just the feature itself is rich or not. And then the title misses, and then if it's rich, relatives, age, if they're poor, or whether they embark in the port S. So those are the maximum 10 features, okay? The 10 feature that it uses. We can change this value to see even further. I leave it up to you, so you can play around with the value here and change and see the other features. Now let's see the logistic regression. So what he thinks about the feature importance. And we can see also here, the most important is the is female feature. Then we check whether the title is master, then the number of relatives, poor and rich, age, and so forth. So it's kind of consistent. We can see always, apart the title master in this case, we always check whether the person is rich in a direct or, if the person is a woman or a man, in a direct or indirect way, and also see whether the person is rich or not. And also we can see the relatives, of the number of relatives occupy a very important spot in the feature, okay? So we can see also here relatives are a little bit more down the line, but still are in the most relevant features. Then it's time to see the best bagging classifier using the decision tree. And also here, again, consistent, we can see that it checks whether the person is a woman, then the title Mr., again, like we saw for the gradient boosting classifier. Again, fair per person, the age, whether the person is poor, relatives, and so on. So you see the scheme, everybody seems to rely more or less on the same features, in a different weighted way though. And finally, we check the bagging classifier using the support vector machine as a base estimator, and we can see again, is female, then relatives, title master, again, title Mr., the age, poor, rich, and so forth. So it's very consistent what all those algorithms think is the most important feature. So they all rely on whether the person is a woman or a man. And then they use the information coming from whether it's rich, how much they spend for the ticket, how many relatives they have, and also the age. So it's kind of in line from what we assumed during the data analysis. And this is a very important step because if we would have seen something completely different, then we might have end up into a bad overfitting. So in this case, we can also see, and it's also good to show in case you want to show to your supervisor or your boss and say, okay, this is the analytics that I found out. Those are my classifiers and those are the performance, and they rely on this kind of feature importance. So it's always good to show alongside the data analysis. Okay, now it's time to do the final prediction. So to combine all what we did so far to make our final prediction on the test data set. So first thing we need to do is to, of course, load the test data set. And as you can see, we load it right at the end. So far we have not touched this data set. And we just remove the unused feature like we did for the training data set. So we removed the passenger ID, but we keep it later aside so that we can recreate the submission.csv file. And then we remove cabin, so passenger ID and ticket like we did for the dataset. And then we plot the information. So here we can see that, again, the feature age has many missing values that we need to fill up. And also there is one missing value for the feature fair. And this is something new because this feature was not missing in the training dataset. So it's also here to be smart and put a meaningful value, even though it's only one missing value. Okay, so then we will start from this missing value from the feature fair. And we need to be careful, as I mentioned. We want our classifier to pay attention to this feature, since we will derive then from it the feature per person, the fare per person. So like we did for the feature age, we have to see what kind of passenger it is, right? So that we can identify how much is likely to spend. We cannot just put some random value also here. So we can execute the code and we can see that the passenger is a poor senior with no relatives, meaning we can use the mean value of the feature fair from the trained dataset with the characteristic of this passenger. So poor senior with no relatives. And this is very important. So now we can, with just this simple line of code, we can see that the value should be 34.4. So what we did here, we took the training dataset, we filter out by the passenger being a man and being poor, with no relatives and the age above 60 years old. And we took the mean value of all the values that we have there. So we use, as you can see, again, something meaningful to replace those missing values. We don't just put some random number inside. Very important. Now we have to fill up the missing values for the feature age. So we must use the same parameters we used before for the training dataset, meaning we cannot again reanalyze everything on the test dataset and then put something accordingly. Instead, we need to use the same data we used for the training dataset. And this is pretty straightforward. The reason why is because imagine this has to run on a production, you want to have this hard-coded. So you want to use these parameters as a reference. So if you have some missing values, you replace based on the analytics, the data analytics that you have done before. Now, of course, if it's in a production, then you want to keep track of updating new data points that are coming in. So these are not going to be hard-coded forever. Of course, as long as you keep on collecting data, then you might modify it and then retrain again your model and so forth. But for sure, you don't want to use only the test data set now to make again all the calculation. So we do like before, we can run everything, and now we can see that again how many missing values, and as you can see, it's kind of the same percentage that we were getting roughly from the training data set. So mostly people from the third class don't have a record for their age. Okay. So, and now as you can see, all of the entries, so all of the data points are filled up. So everything has a value inside and there is no value missing. Perfect. Now let's create the remaining features. Let's start by calculating the number of relatives and fare per person. So like we did before, we combine sibling and spouses plus parent and children feature, and then we divide by the number of those relatives, the fare feature. Then now we have to derive again the title from the name. The title has to be exactly like before, so we cannot use now different titles for our features. So we need to reconstruct the same. And now we can see that we have many misters and then still a good number of misses and miss. And then we have again a master and all the others are miscellaneous. So now we can drop again the feature name since we don't use it anymore. And finally, we one-hot encode the other features. So as we did before, we have where the port where they embarked, and then whether the person is male or not, so the if female person is there, and also the class, so whether it's rich, mid-class, or poor. So we can execute this code. I go a little bit fast here because it's exactly what we did before, so there is not much to explain. And as you can see now, we get the same feature that we were having before. Still using also the original feature, so sibling spouses, parent children, and fare. Why? Because some of our classifiers use only the engineered features, but there is the logistic regression which still uses those entire 18 features. So we need to keep all of them if we want to make the prediction using the logistic regression classifier. So now again, as before, we will reduce the space in memory just to make sure that we don't use much space. And The last step is to rescale the feature the same way we did for the training dataset. So the same scalar that we use during the training on the training dataset, we have to reuse the same and apply it for our new task, so our new dataset. So the scaling method has to be done considering only the training dataset, meaning has to be fitted using the original data, and then we apply this trained scalar onto the test dataset. Why we do this? Because, as I mentioned, the test dataset has to be treated like we had never seen it before. So we use the training dataset to make all our data analysis, all our calculation, also to use the scalar on top of it, and then we apply all what we learned, the same techniques, onto the test dataset. In production, we should do the same, and of course, when we collect more data, then maybe, of course, we can use the entire data again. But never consider the entire data that we also have not seen, because at that point, we don't know when we see some data unseen before how it will perform. So we can execute this code. I hope this does make sense. If it doesn't, you can put some question in the comments down below, and I will reply to you guys. So the final step for this training is to make the weighted prediction using the classifiers we trained before, and finally create the submission.csv file containing all the predictions. So now we will do exactly what we did before. So we predict the probabilities for each classifier. We weight those probabilities by the weights that we figured out before, and then we just simply choose the highest value from these probabilities when we combine all together. So we use the numpy argmax function, and we just pick the highest probability, so whether the person survived or not, combined with all the weights and the prediction of the classifiers. So we can execute this code. Now, for Kaggle dataset, we need to create this submission.csv file in a specific format. That's why I am concatenating the passenger ID with the prediction, because that's the format that Kaggle wants to use to work. So I can run this code and then save this CSV file. So I created a new pandas data frame just with the passenger ID and whether the passenger survived or not. And then I just save with this line of code into my hard disk. So now there is one final thing before making the submission, is to make sure that we are actually getting some improvements. What do I mean by that? So the best case would be, since we tested this random optimization on the training dataset, we also want to make sure that this is really bringing an improvement for the prediction, okay? So what we want to have is to also predict each classifier, to use the prediction of each classifier independently, then upload them, see whether, what are the performance of this single classifier, and then see the performance when all of these classifiers are combined together. So we can do this by simply iterating through each of these probabilities, and again creating a pandas data frame, and then save it with just an index to have a different name. So when I upload, because I already uploaded this before, when we upload our submission files, we get the following results. So the gradient boosting classifier gets 0.78947 of accuracy as a score, logistic regression 0.77, bagging classifier that used the decision tree gets 78.46%, and the other bagging classifier using the support vector machine gets a 77.75% in score. When we combine all of this together with those weights, then instead we get a score of 79%.186, which, as you can see, is higher than each single of them. So then we saw that this makes sense, that helped to get the performance improved a little bit. Now, we still see that there is some penalties. So on the test set, we perform a bit worse than on the training data set. So in this case, now comes into picture what I said before. It should be an iterative process, so we should somehow make some constraints in the parameters of each single classifier, because eventually we are a little bit overfitting onto the training data set. So if we had a data set for training large enough, we would have split it and used then the validation data set, which was a part of the training data set. Since we don't have so much of data, then this kind of process has to be pretty much repetitive. So we will go onto our classifiers and maybe change the parameters when we go with the grid search CV to kind of make some constraints, and then run this part of the program again and see how it performs. So we want to make it perform a bit worse on a training data set and see whether it bumps up the performance on the test data set. Okay, so now we reached the end of this training. The intent here for me was to show you from beginning to end how to solve a problem using a data scientist mindset. I hope this all made sense for you guys. If you have any question, you can ask me in the comments down below and I will reply to you. And I really hope you enjoyed. Let me know your feedback. So thank you guys and see you next time. So that's it for this video. If you guys like my content, you can support me on Patreon, where you can speak directly with me. And also I can give you advice on how to get started into this career. Another way to support this channel is to use my affiliate link that I give you in the video description for your purchases at no cost for you. Finally, another way to support me is to subscribe and share this video on social media. So I thank you for now and I hope to see you in my next video.